Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of stellar evolution. And in the previous video, we described how stars form, we discussed where they form in our galaxy, and described some of the physics of how a star goes from an interstellar cloud to a main sequence star. In that video, the important ideas that go with that is, remember that all stars are formed out of the same materials, hydrogen and helium, and that in our galaxy there are large pockets of hydrogen gas scattered throughout the galaxy. These are giant clouds of interstellar gas. And that the physics of forming a star really involves gravity. Gravity is the force that makes things come together, makes big things into small things. And so in these interstellar clouds of gas and dust, we have quite a bit of gas that will compress and condense down into small pockets of gas. And then the continual gravitational collapse turns these pockets of gas into main sequence stars. And so the idea is that a large cloud of gas can turn into many different stars simultaneously, forming groups of stars at the same time. In this video, what we're going to do is continue to describe some of the details that come with the process of formation. And then we're going to work towards understanding how a star produces the energy that it does. And we'll work our way to the physics of energy production inside of stars. So let's go ahead and get started. So in this video, we're going to concentrate on the idea of how do stars create light. And we'll get there eventually, but we're really on this item right here. And before we can do that, let's talk a little bit about some of the details of star formation. In a previous video, I introduced the Hertzsprung-Russell diagram, and I showed you this version of it here. Remember that the HR diagram, or the Hertzsprung-Russell diagram, will relate many of the physical features of the stars into one diagram, so that knowing the placement on the diagram for any particular star will link together all of these many different physical features. So if you simply know the star's spectral type and you place it in the diagram, you now unlock all these other physical features that come with the stars. And if you don't remember some of those details, I encourage you to look at that video one more time. In that video, we also talked about how the Hertzsprung-Russell diagram can be divided into separate regions where stars share things in common. One of the regions that I had you kind of look and concentrate on is this collection of stars that runs up and down the middle of the HR diagram. All of these dots, all of these stars, share some things in common, and this allows us to put sort of a border around them to make them into one group. And in that video, we called this particular part of the HR diagram, we called it the main sequence. And that's a term that you need to become familiar with. We're going to use it quite a bit throughout the rest of our discussion of stellar evolution. Every one of these stars on this part of the diagram are main sequence stars. Our sun is also on this part of the HR diagram, so our sun is a main sequence star. Now, when stars form, when they finish that formation process of going from cloud, condensing down into stars, the end of the formation process puts them on the main sequence. So a star has to make its debut on the HR diagram on the main sequence. Every one of these stars has a few things in common, and one of the things they have in common is that they have finished the formation process. They are now producing energy at a steady rate, and they will continue to do this for a very, very long period of time. So all of these stars are sort of the equivalent of human adults. Remember in that video we talked about how you take a certain number of years to grow into the adult that you are, but then you're an adult for a tremendous amount of time, the majority of your lifetime, just sort of day to day, not making many changes in your physical appearances. So these stars are all fully formed, and they are now the equivalent of stars that are going to just be adults. They're going to spend the majority of their time doing the same thing, just kind of boring, day in and day out, producing energy. Eventually, the stars on the main sequence will leave, and they'll move up to this part of the diagram. And we talked about how these are stars that are dying, and then the stars down here are stars that have finished the evolutionary sequence, and these are stars that have died. Now, we'll get to those eventually. But when a star finishes its formation, it is now a main sequence star. And it will stay on the main sequence for an enormous amount of time, just steadily producing energy. Let me show you an example of a group of stars that have finished the formation process. This is a cluster of stars. It's a very famous one. It is called the Pleiades cluster. And the reason why it is very famous is because this is a cluster of stars that you can go outside, and as long as you're outside at the right time of year, you can see this cluster in the sky with your own eyes. There's no need for a telescope or any sort of a magnifying device. It will look in the sky as if there are 7 stars that are together in one tiny group or cluster. And the reason why it is called the Pleiades cluster is because the 7 stars that show up, that are visible to the naked eye, are named after the Pleiades sisters from ancient Greek mythology. These were the 7 daughters of the Titan Atlas. So the 7 sisters of the Pleiades. And in reality, when you look at this cluster through a telescope, what you'll notice is it is many, many more than just 7 stars. It is actually about 250 stars, only 7 of which are bright enough to be seen without a telescope. These are stars that formed together as a group. So every one of the stars in this cluster, they are siblings to each other. They're all the same age, they all formed at the same time, and they're together as a group because of their formation. And the cluster itself is slowly moving through the galaxy. So think of it as all these stars together as one collection, moving through the galaxy as a group. Sort of like a group of people standing together, all together as a group, but slowly walking together. These stars are moving through the galaxy like a group of people would move across the room. Now, as these stars move through the galaxy, what happens though is their movement will slowly make the stars wander off. So right now, these 250 stars are together, but their slow movement through the galaxy is going to make them slowly drift apart. And maybe after 2 or 3 trips around the galaxy, this cluster of stars will no longer be a cluster. They will drift apart. So these types of clusters are called open clusters. And the reason why is because they're gravitationally open, meaning gravity will not hold them together as a cluster forever. They will eventually wander apart. So the cluster is open, meaning that they can wander away. The stars in the Pleiades cluster are about 100 million years old. And to a human, that sounds enormously long, but 100 million years is actually relatively young. These are stars that formed fairly recently, and again, are some of the youngest stars in our galaxy. So all of the stars in these clusters, this Pleiades cluster as an example, are on the main sequence. These would be stars located on this part of the diagram. Now, the second thing that makes all of the stars on the main sequence have something in common, the second thing they have in common, is that they're experiencing a phenomenon called hydrostatic equilibrium. Now, this is a very large phrase, big mouthful of things to say, hydrostatic equilibrium. And so what I'm going to show you is what this means, and then of course I'll show you the reason why this is an important idea. Let's imagine we could take the sun and we slice the sun in half. So you take it and slice it. Here's the surface of the sun. This is getting deeper and deeper and deeper. And then now we've reached the middle of the sun. This part that you see right here in white, this is called the core of the sun. And it is the place where the nuclear reactions, where the energy being produced is coming from. So this is the energy source location inside of the sun. The energy that's being produced inside of the sun has to work its way out before it can go off into space. So quite literally, the photons of light that are generated in the sun will slowly work their way to the surface, and then they go off into space, and that's what you see when you see the light from the sun. However, the light that is made at the center of the sun, that light has to push its way through the outer layers. So the energy that's made has to get out by working its way through these outer layers. And what that does is that creates what's called radiation pressure. So radiation pressure is the pushing or the pressure of the energy working its way out to the surface and then out into space. If left by itself, radiation pressure would make the sun become bigger and bigger very slowly as time goes by. In other words, the pushing of the energy would make the sun become physically larger in size. Now, On the other hand, gravity, the sun's very, very large mass and tremendous amount of gravity, the force of gravity is acting to make the sun become smaller. The force of gravity is working to shrink the sun. Very slowly over time, the force of gravity would make the sun smaller and smaller and smaller. So what we have are two opposing forces, radiation pressure working outward and gravity squeezing inward. Now, because we know the sun is not shrinking and because we know the sun is not growing, what we know is that there's a balance between these two forces. So hydrostatic equilibrium is the balance between the radiation pressure pushing out and the force of gravity squeezing inward. And as long as this pressure outward is balanced by gravity inward, the sun is very stable. It won't shrink, it won't grow, it produces energy for a very long period of time, and it just steadily does this year after year after year. But between these two forces, radiation pressure is ultimately going to lose because gravity never goes away, but the ability to produce energy won't last forever. And we'll come back to that idea in a few minutes. Now, what I'm going to do is relate this sort of to the big picture. What I have is another HR diagram, but this time I'm only going to show luminosity and surface temperature, and I'm only going to include the main sequence. What I have on this diagram is a listing of the masses of the stars as we go down the main sequence. And you might think, how do we know the masses of these stars when this doesn't say mass and this doesn't say mass? If you remember from a previous video, there was what's called the mass-luminosity relationship. And that is, stars that are more massive are also stars that produce more energy or are more luminous. So if this star up here is very luminous, it therefore has to be also very massive. So this star would be a 40 solar mass star, meaning it's the equivalent of 40 times the mass of the sun put together. 10, 8, 3, and then you can see 1 down to 0.5. Now, these numbers are indicating that as you go down the main sequence, the masses of these stars are different. The highest mass stars are up here, and the lowest mass stars are down here. Now, what does this mean? Well, over here on the left, you see it says pre-main sequence timescales. What that means is, how long does it take for the star to go from a cloud to the main sequence? In other words, how long does it take a star to form? What we now know, let's put some numbers up, is that the number of years needed to go from a cloud to shrink down into a star depends on the mass of the star. Notice the numbers in red are in years, but notice the numbers are getting bigger as we go down the main sequence. So what that means when you put these two things together is stars up here that are the highest mass stars in our universe take the shortest amount of time to form. Stars down here take longer because they're less massive. Stars down here take longer and longer and longer. So ultimately what we know is the mass of a star is going to determine how quickly or how slowly the star forms. Stars that are high mass form quickly, notice the numbers are shorter, and stars that are low mass form slowly, notice the numbers are bigger. So a star that might be 40 solar masses takes somewhere in the neighborhood of maybe a few thousand or a 10,000 year period of time to form, but a star that's only half the mass of the sun might take something in the neighborhood of 100 million years to form. So 100 million years is a tremendous amount of time. Now you might be thinking, why is this? Why does a star of greater mass form quickly, but a star of lesser mass form slowly? And the answer has to do with gravity. Gravity is the force that makes the cloud shrink down to the star. And so if you have a tremendous mass, you have a powerful gravity. And so that collapsing down to make the star happens quickly because gravity is powerful. If the star's mass or the cloud's mass is small, the force of gravity is weak, and so it takes a much longer amount of time for that weaker force of gravity to end up making a star. So what we now know is the period of time that it takes a star to form is dependent on its mass. Higher mass, shorter amount of time, lower mass, longer amount of time. Now what we're going to see in the next video is how stars produce their energy, and what we're going to learn is that gravity plays a major role as well. But we're just about out of time in this one, so I hope you'll join me in the next one. We'll see you then.